Okay, so for today, what we're looking at, we're diving into probably our last section. We're going to be, put this in perspective, we're going to be extending everything we did in Unit 4 to Unit 5, that we did with quadratics to bigger polynomial equations. So we're going to focus a lot today on the fundamental theorem of algebra, which we've already talked a little bit about. Just says a polynomial of degree n has exactly n complex solutions, guaranteed, no matter what, it always does, including multiplicities. So if some of the zeros have higher multiplicities than 1, they just count for multiple solutions is all. If a solution has a multiplicity of 3, it counts as 3, okay? So really what we're doing then is same stuff we did last unit. We're going to always put our polynomial equations into standard form by setting them equal to 0. And then our goal is to find all the zeros of that polynomial equation by factoring, okay? And so we have to extend what we did last time to bigger polynomials. Let's do just a little quick review of Unit 4 stuff, just so we can get, we can really familiarize ourselves and have firm foundation, good footing going into this next stuff. How would I solve this quadratic equation? Set it to 0. So push everything to the left and just get that, right? How would I solve? So once I get it equal to 0, it's in standard form. What would be the easiest method to solve that? Magic numbers, right? I mean, we could use quadratic formula, of course. We can always use quadratic formula to solve any quadratic equation. But they're pretty simple magic numbers. What are magic numbers that multiply to negative 14 and add to negative 5? Annika, can you find those? Multiply to negative 14, add to negative 5. I'm putting you on the spot. Negative 7 and 2, very good. Okay, so we got negative 7 and 2. And that helps us a lot, right? By factoring this thing, it gets easy to solve. I couldn't, other than using the quadratic formula, I really had no way to figure out what values of x were going to make those three terms combine to 0. But now that I've got it factored, zero product property makes this simple. The product of the first factor and the second factor can only equal 0 when either one of those is equal to 0. I only multiply to 0 by multiplying by 0, right? So one of my solutions then, 1 0 of this function, if I were the function that's set equal to 0, 1 0 of that function is going to be the 0 of the first factor. What is that? 7, right? And if I plug 7 in, I would just get 0 times 9 is 0, right? It works. What's my second 0? Negative 2. And if I plug negative 2 in, I would just get negative 9 times 0 equals 0, right? So I got them. I got 2 real zeros of this purple function. So where would the x-intercepts be of this thing then? 7 and negative 2, right? Real zeros of a function always correspond to x-intercepts. So if I graph that purple function, I know it's a parabola that's opening up and it's got x-intercepts at negative 2 and 7. No big deal, okay? All right, let's try another one. How about one like this? How did we solve that in Unit 4? We had a couple ways we could do it, but what's a way to do that one? Yeah, I can point to a single x so I can isolate it, right? Now, that always works for quadratics, okay, but we're going to see we run into some difficulties when we try to extend that to bigger polynomials. We'll try that in a little bit today, and we'll see we have a little bit of a problem. But it works for quadratics. So if I can point to this single x, so I can isolate it, add the 4 to both sides, square root both sides, right? And that gives me x equals, what happens if I square root both sides of an equation? Plus or minus, good. So I just get plus or minus 2. Okay, I get 2 real solutions again. And so again, if I were going to graph this purple function that's being set equal to 0, it's got x-intercepts at -2 and 2, right? Okay? What's another way I could have done this one? There is an alternate method, right? I could also, factor that as a difference of squares, couldn't I? Right? X squared minus 4, I could think of as x squared minus 2 squared. And how does a difference of squares factor? And what is x squared minus 2 squared written in factored form? X minus 2, x plus 2. Exactly. And then I'm going to get the same solutions, aren't I? I'm going to get x equals 2 or x equals -2. Either way, right? Okay, good? How about this guy? That one doesn't factor, right? Because there is no sum of squares pattern. I can't do x squared plus 2 squared. There's no such pattern. So this is one where I would have to just isolate the variable. There's my x. So if I subtract 4 from both sides, and then I square root both sides, I get x equals, I got to have my plus or minus, right? Because I'm square rooting both sides. But what do I do with that negative inside the radical? It becomes an I outside. Good. So I get plus or minus square root of 4, which is 2, times I. Okay, is this one going to have any x-intercepts? No, because there are no real zeros, right? X-intercepts are interchangeable with real zeros. They always go together. So what's this graph going to look like? What do you think, Aubrey? If I'm graphing this quadratic here, so here's the function I'm graphing. It's quadratic. It's got to be a parabola that opens up. But what can you tell me about the placement of the vertex if my solutions are both imaginary? What do you think? We said it can't have any x-intercepts. So if it's opening up, I'm not being very clear with the question. Relative to the x-axis, where does that vertex have to be? Not on it, right? Because that would be an x-intercept, right? It's got to be above it, doesn't it? Does that make sense? Because we can't have any x-intercepts, so it's got to be up above it. It's got to look, there we go. It's got to look like that, something like that, right? Where I don't get any x-intercepts because I had no real zeros, okay? All right. How about one like this? More review. What do I do there? What am I doing there? Hayden, if I'm solving this one, what am I doing? What am I doing to that one? Well, I can't isolate it because I've got x squareds and x's, right? Set it to 0, though, right? So I got to push the 4 over to the left side. So I got x squared minus 2x plus 5 equals 0, right? So now I got to find the zeros of this polynomial, this quadratic polynomial. Only this time, can I find magic numbers? Doesn't factor. Okay, but that's okay, right? For quadratic expressions, I don't have to factor quadratic expressions to solve them. I can always just go to the ace in the hole, which is the quadratic formula, right? So remind me real quick, if I've got a quadratic equation in standard form, so ax squared plus bx plus c equals 0. Warm up your singing voices. What does the quadratic formula tell us? X equals all divided by 2a. Okay, so there's our quadratic formula. What are our values of a, b, and c in this trinomial? 1, -2, 5. Good, okay. So then if I'm going to apply the quadratic formula, I'm going to get -b, which is what then? 2 plus or minus the square root of what? 4. -2 squared is 4, right? 4 minus 4 times what? Times 1 times 5. All divided by 2. Okay, so I got to simplify that. 2 plus or minus the square root of 4 minus 20 is negative 16, right? All divided by 2. Okay, so that's giving me 2 plus or minus, what's the square root of negative 16? 4i, okay. So then I could split that up into separate pieces, couldn't I? If I split that up into separate denominators, 2 over 2 reduces to what? 1. So I'm getting 1 plus or minus 4 over 2 reduces to 2. And then I've got an I in that second term. Okay, this is important, right? When we get solutions to a quadratic equation, if I get solutions that are not real, I'm getting imaginary ones, right? And they always show up in pairs. In fact, they always show up in pairs that look like this, in complex conjugate pairs, no matter what. 1 plus 2i and 1 minus 2i form a complex conjugate pair. The only difference is just the sign of the imaginary part, right? Positive in one case and negative in the other. But the real part's the same both times. So that's a really important relationship that we have. Complex conjugate root theorem. It just says that if a plus bi is a 0, then a minus bi is a 0. For sure, they always go together. Complex solutions with imaginary parts always come in conjugate pairs. Always. You can never get a singleton. They always come in pairs. So if I graph this one, I'm going to get a similar graph. I get no real zeros, so I get no x-intercepts. And the parabola opens up, so the vertex has to be above the x-axis, right? Okay, so I want to, one other thing I'll just mention. So in that last example, I just told you that imaginary solutions always come in complex conjugate pairs. Well, in the last example, we got the solutions plus or minus 2i. That doesn't look like a complex conjugate pair immediately, but if you think about it, it is. Couldn't I write plus or minus 2i as 0 plus or minus 2i? So the real part is 0, and the imaginary parts are just plus 2 and minus 2, right? Everybody see that? So they are complex conjugates. They have to be. So I would like you to tell me then, for a 5th degree polynomial, if the degree of the polynomial is 5, how many complex solutions are we guaranteed to get? First of all, 5. Absolutely. We know we've got 5 solutions, just that some of them might be imaginary, right? Okay, what are the possible outcomes here? I want you to tell me, what are the possible combinations of real zeros and imaginary zeros? Like, I want to know, like, I could get, what number of each type could I possibly get? What's one outcome that would work, that I could get? 5 real and 0 imaginary would work, wouldn't it? Oh, darn, I keep doing that. I mean to do this. So 5 real and 0 imaginary, I could get that outcome. Could I get 4 real and 1 imaginary? No, I can't, because the imaginaries have to come in pairs. So what's the next possibility I could get? 3 and 2. Okay. Okay, could get 3 real and 1 pair of 2 complex conjugates, right? And then the only other possibility, 1 and 4. Okay, good. And so I have to get, for an odd degree polynomial, I'm always going to have to get at least 1 real 0. Now, doesn't that make sense if you think about the end behavior? If the end behavior of an odd polynomial, it either has to do this or this. So if it's going up and down forever in both cases, it has to cross through the x-axis at least once, doesn't it? Because it's going all the way from positive infinity to negative infinity and everywhere in between, right? The y values. Okay? How about this one? What am I going to do? Got to solve that equation. What do I always do? First step is kind of a no-brainer. What do I always do? Set it to 0. Yeah, subtract 2 from both sides. Okay, we could use quadratic formula, but we always want to try. Magic numbers are so much easier if we can find them. Do they exist here? Ella, can you tell me magic numbers that multiply to +1 and add to -2? Yeah, -1 and -1, right? So we've got the factors x minus 1 times x minus 1 equals 0. So what are my solutions? 1 and 1, right? There's only one specific value, but it shows up twice. It actually counts as two solutions because it came from two factors, right? So what's the multiplicity? I get one solution, x equals 1. The multiplicity of that solution is 2, okay? An easier way to see that would be to write this as the quantity x minus 1 to what power? Squared. Yeah, x minus 1 squared equals 0. So I only get one solution, x equals 1, but the multiplicity is 2. So it counts as a double. So I still, in other words, the fundamental theorem of algebra still works. It guarantees two complex solutions, and we got them both. They're both x equals 1. It counts as 2. That you might potentially be thinking, okay, well, what's the difference between that, getting x equals 1 one time, or getting solutions like +2 and -2? Well, there is a difference, right? What did we say about multiplicities in graphs? Higher multiplicities actually are different solutions. When we get multiplicities of 1, right, these are both solutions with a multiplicity of 1, then the function cuts through like a line. It cuts through the x-axis. But what's it going to do here? If I have a multiplicity of 2 at my x-intercept of 1, it's going to look different. What's it going to do? It's going to bounce, yeah. And so we can even see it in the graph. Multiplicity of 2 is fundamentally different than a multiplicity of 1, okay? All right, give me 1 to 5. How are we doing? Okay, any questions? Anything you could ask me that would, like, is a part you need clarified? Okay, probably just takes more. We just have to keep talking more. And gradually it just gets clearer as we continue discussing it. So what about this guy? What's already set to 0? What do you know? Already set to 0. First for everything. Okay, so this is one that I can't factor, right? No magic numbers exist, so I've got to use the quadratic formula. So what's that going to give me? X equals what? 1, good. Plus or minus square root of 1 minus 4 times, well, okay, 4 times what? Times 1 times -11. Okay, divided by 2. Okay, but notice here, if I'm subtracting a negative, I have a multiplying an even number of negatives, they cancel and I get positives, right? So then I'm actually getting, for this, x equals 1 plus or minus the square root of 1 plus 44 all over 2, right? What does the square root of 45 simplify to? 3 radical 5, right? Because I could split that into 45. That's pretty good. But how do we get that? You're just thinking about it in terms of, if you think about it, now maybe we can start to speed up that process a little bit. Instead of going through the whole factor tree, you could maybe think about this as just, couples go out, singles stay in is how we always talked about it before, right? We could factor this into a 9 and a 5, and the 9's going to break up into a couple of 3's, right? So I'm going to get couple of 3's, the 3 goes out, single 5, the 5 stays in, right? So I'm going to split this up, split the denominator, so I get 1/2 plus or minus. My outside number is a 3, and my inside number is a 5. But there's another way to think about that. You can get there quicker. We want to just think about what's the biggest perfect square factor of 45, and that's 9, isn't it? So we can break the square root of 45 up into, that's supposed to be a 45. You can't read that. 45. We can break it up into the square root of 9. There's the biggest perfect square factor, right? Times the square root of 5. And so that's giving me my 3 radical 5. Everybody see that? You don't really have to do the couples go out, singles stay in. Just think about breaking up the number into a perfect square and whatever the other factor is. Okay? Okay, I want you to notice something here. So there's another important kind of a relationship going on that gives us some clues as to the nature of the solutions of these polynomial equations. When we get an answer, I got real solutions here. There's 2 real solutions. If I get real solutions that are irrational, if they have square roots in them, notice that these also always show up as conjugates, right? I got 1/2 plus 3 radical 5 over 2 and 1/2 minus 3 radical 5 over 2. Now, they're not complex conjugates. There are no i's there, but they're still conjugates. They still fit that conjugate pattern. So we have another relationship, the irrational root theorem. So if a polynomial, and there is kind of a caveat here, if a polynomial has rational coefficients, so this only works if the coefficients in the original polynomial, the numbers being multiplied by the powers of x, are not irrational. They have to be rational numbers. If they're irrational, so if they include things like square roots, then this doesn't hold. This wouldn't apply. But if the polynomial has rational coefficients, and most of the time polynomials we deal with do, not always, but most of the time they do. If that's true, then it's telling us that if we get solutions that involve square roots, they always come in complex conjugate pairs every time. Okay? Why is that useful? You might be wondering, that seems kind of arcane a little bit. Here's why that's useful, just a little peek ahead. What if I told you I wanted you to do something like build the simplest polynomial? So we're implying that we're going to have rational coefficients. With zeros x equals 2, and how about x equals 1 minus the square root of 3. How could I build that? I should be able to turn each of these zeros into a factor, right? If I work backwards. And we haven't gotten it. We're going to do this later. But you guys see that the factor that goes with x equals 2 would just have to be x minus 2, right? And we'll talk way more about this in the future. But you getting an idea? That makes sense? Like we're just working in reverse. Normally we would get the solution x equals 2 by having the factor x minus 2 and setting it equal to 0, right? Okay? I would get another one from this guy, but then that's going to be a mess because I'm going to end up with x minus something involving square roots, right? How would I get those to go away? And this is pretty, if this doesn't make total sense, don't panic. I mean, we have a lot more talking before we actually do problems like this. But where this last theorem comes in handy is it tells me that if x equals 1 minus the square root of 3 is one of my real zeros, then can anybody tell me what another one has to be? 1 plus the square root of 3 by this irrational root theorem. And when I take both of those together, it makes it a lot easier to reverse engineer this polynomial than it would if I just had one of those things, right? Okay, and in fact, the only way that I'm going to get a simple polynomial with rational coefficients is if I do include both of those. So the only reason I'm bringing that up, I don't expect that to make sense totally right now, but I just want you to see that there is a rationale for talking about this, right? That it's important that we can link these real zeros together, that if I get one, I'm guaranteed to get its partner with it, okay? All right, I don't want to spend more time on that though. We'll get back to that stuff later. Okay, here's where I want to end up for today. Let's look at this example. So x cubed minus 8. Now we're gonna ramp up and we're gonna start solving some bigger polynomials, cubics, not just quadratics, cubics and quartics and bigger, higher degree polynomials. How could I approach that? How could I solve for x there? Suggestions? Okay, I could just isolate the x, couldn't I? I could take the same approach that I took right there in this one. We just pushed the 4 to the other side and square rooted both sides and got both of my two solutions to my second degree polynomial. It worked great, okay? I could try the same thing with this cubic. Let's add the 8 to the other side. Let's cube root both sides. Okay, but when I cube root both sides, if I cube root a number, if I'm solving an equation by taking an odd root, a cube root of both sides, cube root is an odd root, it's a third root. Square root is an even root. A square root is really a second root, right? Whenever I take an even root of both sides of an equation, I have to include plus or minus, okay? Because, and the reason for that is because both positive 2 and negative 2 squared are equal to 4. If I take a negative number to an even power, it always ends up being positive, doesn't it? Is that true for an odd power? If I take a negative number to an odd power, does it become positive? No, it stays negative, doesn't it? So here's my question then. Along those lines, do I need to include a plus or minus here if I'm cube rooting both sides? I don't. I only end up getting one solution out of this. X is equal to, what is the cube root of 8? 2. Because 2 cubed is equal to 8, right? Negative 2 cubed is not equal to 8. So I can't include the negative, it's incorrect. Okay, that's good. I got a solution, but what's the problem with that? I started off with a third degree polynomial. How many solutions are there? 3. There are 3 complex solutions, and I only got one of them. Now, the good news is I got the only real solution, which is 2. If I were to graph this function, here's the graph. It only has one x-intercept, and I found it. The bad news is I did not get the 2 imaginary solutions that come as a complex conjugate pair. I missed them, right? So you can find the real solutions of any polynomial by isolating the variable when you can, okay, but you're going to miss a bunch of imaginary solutions. So how do we get those guys then? We need the other 2. Well, here's how. We've got to use a factoring pattern. Okay, we're going to add some new factoring patterns. We have 2 from last unit. Really only 1. We know that a difference of squares pattern, a squared minus b squared, always factors into a plus b times a minus b. And a sum of squares pattern doesn't exist. A squared plus b squared doesn't factor. We have to do corresponding stuff now for cubes. We need to find the sum of cubes pattern and the difference of cubes pattern. Okay, these are really easy to do. I don't know what happened there. That was weird. Here, let me... There we go. Okay, so if I want to do sum of cubes or difference of cubes, here's how you can remember these patterns. They look complicated, but they're not. Here's how. You always know that both the sum of cubes and the difference of cubes is going to break into 2 different factors, one simple binomial factor and one more complicated trinomial factor. The binomial factor always has the terms a and b, and the trinomial pattern always has the three terms a squared, a times b, and b squared. The question is just, what are the operations that go between those terms? Are they pluses or minuses? Here's how it works. Really simple. If we're doing a difference of cubes pattern, so a cubed minus b cubed, here's how it goes. Well, the operation that goes in the binomial is always going to duplicate what the cube pattern is. If it's a difference of cubes, then the first operation is minus. The second one flips, it's the opposite, so it's going to be plus. And the third operation in this pattern is always plus, no matter what, it never changes. Okay? So what's going to happen then if this is a plus, what should that be, do you suppose? Plus, because it's going to match, follows the same pattern. It's going to match what's there. What's that one going to be? What do you think? Allie, what's it going to be? It's going to be negative because it's got a flip, doesn't it? So it's going to be negative, and that one's always positive. Okay? There it is. Those are our patterns. Okay? No big deal. All right, so let's use that pattern now and redo this problem. The question is, can I rewrite this as a difference of cubes? Can I? Can I rewrite this as something cubed minus something cubed equals 0? What's the other something? Well, I got an x cubed minus what cubed? 2 cubed. There we go. Because 8 is just 2 cubed, right? So now I just have to follow my pattern. A cubed, I'm going to use the a cubed minus b cubed pattern, right? Okay, so Trey, what's this pattern? See how well you got this. What's the binomial factor going to be? I said Trey. But I meant Cray. What's the binomial pattern going to be? Okay, help him out, Trey. Okay. Melanie, you're on the spot. You got this. Annika, you got this. See, I knew you had it. What is it? You got it. So okay, yeah, so what goes in there? That was an a and a b. That's a minus. Okay, so what are the terms in the trinomial? Let's put the terms in first. A squared plus, good, ab plus b squared. Good, there it is. Good, right? Okay, so now there's our pattern. We just have to apply that down here with x cubed minus 2 cubed, right? This is really simple. Instead of an a, what do we have? X. Instead of a b, we have a 2, right? A cubed minus b cubed becomes x cubed minus 2 cubed, right? So we end up with x minus 2, right, equals x squared. That's bad x squared plus, what would a times b be there? 2x, right? X times 2 we would write as 2x plus 2 squared, which is 4, yeah. Okay, so now we got it factored. Okay, this is going to give us different, more complete answer, isn't it? Because now I've got my x cubed minus 8 factors into this, which is all equal to 0. So if I apply the zero product property, yes? No, okay, good. I'm glad you asked that. On our pattern over here, let's go back and look at these patterns for a second. This time we're separating out. I know what you're thinking. You guys are thinking of when we did the binomial expansions. Guaranteed. You're thinking of stuff like this. Like what if we had, you're thinking of a plus b quantity cubed, for example, right? And you're thinking of that if I was trying to apply that to something like this, x minus 2 quantity cubed. Everybody see that? So that means a is x and b is negative 2, right? Because I'm forcing addition in this situation. I'm saying I'm always adding a plus b. So x minus 2 is x plus negative 2. Okay? For the binomial expansions, we didn't want to have to include an extra formula for a minus b cubed. We just always did it as a plus b, but b could be negative. Okay, with these patterns, we don't do that. We have separate patterns for a cubed minus b cubed and a cubed plus b cubed. So the b is always going to be positive. But either we're subtracting it or we're adding it. Yes?
What's making it plus ab instead of plus 2ab?
Okay, so because it's a different thing. This is not the same thing as saying a plus b quantity squared. I know it's confusing because they look similar, but this is not the same thing as the expansion of a plus b squared. This one it doesn't have the coefficient of 2 in these sum and difference of square patterns. There's no real profound reason for it, it's just the way it works. Okay? So then going back to this example, okay, so the one we're working on, this is literally x cubed minus 2 cubed. So let's write down what our values of a and b are. So a is equal to x and b is equal to 2 because b is, how do I want to say this? Because I'm subtracting 2 cubed. And 2 takes the place of b in our a cubed minus b cubed pattern, right? You get that? So the b is not negative. When we're using these patterns, b is always positive. But in one case, we're subtracting b cubed, and in one case, we're adding that positive b cubed. Okay? Does that make sense? That's why we wouldn't the question was, why wouldn't we make that b a negative 2? Because it's not. It's positive 2. It's always positive. Okay? We're just subtracting the second term this time. Okay? So we got this thing factored. You'll get a lot of practice with that. You'll iron out the kinks when you get an assignment and get to practice this a bunch. So now we can apply the zero product property. We've got these two factors. This is the last thing I want to get through. So the first zero is easy. We get x equals 2, which is the same one we got last time, right? We got x equals 2, which was our one real zero. That's our x-intercept. But look what else we're getting here. We're getting this quadratic factor. We got to find the zeros of that. You might be tempted to try to factor it. Don't waste your time. It's never going to work. When we use these sum and difference of square patterns, no matter what, every time the quadratic factors, the trinomials, are always going to be irreducible quadratic factors. Which means they will never factor and they will always give us back imaginary solutions. Well, they're always going to get a complex conjugate pair of imaginary solutions from those trinomial factors we get in these patterns. Never going to be real, always imaginary. They always yield complex conjugate solutions. So don't even bother trying to factor them. Just set it equal to 0 and solve using the quadratic formula. It's the only way to do it. So from this factor, we just set that equal to 0 and solve. Okay, well, we use the quadratic formula. X would equal negative b plus or minus the square root of b squared minus 4 times a times c all over 2, right? So that's giving me, I'm just going to go fast because we're getting close to the end. negative 2 plus or minus the square root of negative 12, right? Over 2. So if I split up my denominator, that's giving me negative 2 over 2 plus or minus. What does the square root of 12 simplify to? 2 radical 3, right? Because I can break it up into the square root of 4 times the square root of 3, and the square root of 4 is 2, right? And I need an I. You're right, need an I. And so then if I reduce the fractions, I get negative 1 plus or minus the square root of 3i. Those are the other two solutions that we were missing before, right? They're complex conjugates. They don't show up as x-intercepts, but they're still solutions. They're still zeros, right? Okay, that's a good place to stop.